But what really sets the magma chamber simulator apart is that we do this 3-in-1. So we have melts for the magma chamber, a melts for the wall rock around the magma, and then a melts for the recharge, anything that might mix in. The first step is that the wall rock will prime and try to figure out exactly what it's going to be like at every temperature throughout the run. Then we press go, and the magma can cool and crystallize. It goes from the liquidus temperature, and as it starts to cool, heat from the magma goes into the surrounding wall rock, if you remember back to our diagram. And this will actually heat the wall rock up until some temperature, until it starts to actually get warm enough to melt. Remember what I said about them talking to each other? Once the wall rock has warmed up enough to actually melt, it can produce some extra partial melt, and then it will transfer that partial melt to the magma. So again, we have different versions of melts, and they're actually talking to each other. Once the magma has taken in that new melt, it changes its composition, and then it can cool and crystallize. As the magma cools, it's kind of hard to see because it's so small, but the magma temperature is decreasing and the wall rock temperature is increasing. Finally, we have a recharge. Recharge introduces more heat into the system, changes the composition of the magma again, and allows it to cool and crystallize some more. Finally, we'd export our data. The output file for our majors, remember, it's the input file for our traces. Pick out the trace elements and isotopes that you would like to model. You pick in your partition coefficients, check the values and make sure that they're all correct. And again, you check them for each individual subsystem and press go. The magma chamber simulator will use the partition coefficients that you've selected and the mineral assemblage that was produced to calculate the new ideal trace element composition for your magma.